welcome to this tutorial. We're going to talk about image compression. Well, first of all, image compression is to actually reduce the physical size of an image. This means to reduce the amount of data, but keeping the necessary information in order for the image to not be distorted or to not lose some kind of data or information that we want. For example, if our picture, the size of the picture is 100 kilobytes, we can compress that size to get 80 kilobytes, for example. And well, we need two things. First, we need to know the data. The data are the codes that represent the value of a pixel. And the information. The information is the interpretation of this data. And well, actually there are two methods for this. We can divide it into symmetric and asymmetric methods. Well, first of all, the symmetric methods, the characteristic of the symmetric methods are that the compression time and the decompression time are the same. This means that the same process for compression is used for decompression. Now, with the asymmetric codes or methods, the compression time is larger than the decompression time. So this means that when we are going to compress a movie or an image, we need to know how big, how long it will be to compress and to decompress the image. Now, in order to do this, we need to use a codifier. The codifier is an algorithm designed to compress only a specific value of data or type of data. And we have three types of codifiers: the non-adaptive, the adaptive, and the semi-adaptive. In the non-adaptive, the input of the image, it's based on previous knowledge. For example, in medical images, we know that bone and tissue only works with a specific window of colors, of grayscale values. So we will use an adaptive method to determine only the one window if we want to see bone or any other structure. Now, the adaptive one, it creates a dictionary as the code runs. This means that it creates all the data and all the information as the algorithm reads the image. Now, in the semi-adaptive, we have one dictionary that is generated as the code runs, and another one that we previously established. This semi-adaptive codifier is the combination of the non-adaptive and the adaptive one. Now, the types of compression. There are two types of compression: the loose compression and the lossless compression. As we can see in here, the lossless compression is actually a way to compress without losing any kind of data. We can have our original image, then compress it, and then restore it at its full, without any information lost or data lost. And we have the loose compression. On the loose compression, we have an original image, then we compress the image, and when we restore the image, we have information lost or data lost. We will start with lossless compression. Lossless compression, well, actually these two methods depends on the field of application. In lossless compression, we need to use it when the application it requires to be as accurate as possible and without error or misreadings. So we will use a lossless compression. For example, in the medical imaging, we will need every data of the image that can be significant because if we don't do this correctly, we won't be able to locate certain spots or certain pathologies inside a medical image. And because of this, because of the complexity of the lossless compression algorithms, they are greatly demanding because the lack of information loss. Now, there are several codification methods, lossless codification methods, and according to the functions and characteristics, these can be described as variable length codification, Huffman codification, and the bit planes codification. First, we will see the variable length codification. The variable length codification is actually, it consists in taking the probability of each symbol or character that appears in an image, and to that probability give him a name tag, in this case a code. The characteristic of this code needs to be that the ones with the high probability corresponds the shortest code. In this example, we can see that the symbol 0 has a probability of 0.6561 and the code length is 1. And the symbol 15 has a probability of 0.0001 probability of appearance and the code length is 10. A characteristic and a specification of these codes is that they need to be in zeros and ones. So, taking this into account, we will see now Huffman. The Huffman method was designed by D.A. Huffman in 1952, and it's actually it uses the statistical distribution of the grayscale levels of an image, and then it generates code that gets you closer to the minimum theoretical limit. This minimum theoretical limit is all called entropy. In here we can see, in this image we can see an example of a Huffman encoding tree. As we can see, it uses zeros and ones to represent the data codes. It's a variation of the variable length codification. This gets clearer when we see the steps that we need to follow to do Huffman. The first step is taking the frequency of each level of the grayscale image and calculate its probability. We can do this using the histogram function. Then we will order them from the most probable character to the less probable character. Then we will add the two less probable characters, and we will repeat this step until only two probabilities remain. After that, we will generate the codes, alternating ones and zeros. As we can see in this example, the first step, we will check the pixel value and get its frequency. To take out the probability, as we can see, the 1 pixel value has a frequency of 160. It gives us a probability of 0.4. We will arrange them as we can see in the step number 2. Then we will add the less probable characters, 0.1 and 0.2. Then we will repeat this, we will reaccommodate the numbers, the probability numbers, and add the less probable numbers again, until just 2 values are left, and then we will arrange them from the most probable to the less probable. After that, we will backtrace the tree, alternating symbols, codes, zeros and ones, as we can see in step number 5. This means that if we have the original size of an image of 12 bits, if we choose Huffman, we can change the size of this image to 8 bits. This occurs because we can compact the sets of data with the most probable information and give them just a code tag of a short value, of a short information number. So this is how we can use the Huffman method to compress an image. The second part of the lossless compression methods, it's actually the bit plane. It's called the bit plane encoding. The principle for this method, it's actually pretty simple. It just consists on separating an image in a multi-level image. For example, we have an 8-bit image. We can decompose them in images of 8 images of 1 bit, and then treat them as a series of binary image, and compress them, separate them, then decompress them together. This is a very easy to explain method because it just depends on the number of bits and the number of images that we are going to compress. But the first complication or problem of this method is actually that we can have errors when the most significant bits are practically the same. For example, we had the 128 number, value, data value, and in another plane we have 128 value and then a 127 value. This method will actually think that they are the same plane, so we will have a little bit of data loss. So the only thing to take in consideration with this bit plane encoding method is to actually be certain that the image, the values of the image are not so close together, so we can have an optimized way to separate this image and compress them. Now, for the loosely compression, the loosely compression actually, what it tries is to have a good ratio between the tolerance error and the data reduction. This means the amount of data that I'm going to lose versus the size reduction that I will have. And well, actually, we can obtain, we can resize an image from, for example, 100 to 1, and still keep the image recognizable. But if we have rescaled the image from 10 to 1 or from 15 to 1, 50 to 1, we would see that the images are not recognizable, are unrecognizable. This means that the loosely compression method works best when we have bigger images. As we can see here, we have two types of loosely compressions. The first one is called loosely compression with predictive coding, and the second one is called the transform coding. The loosely compression methods or algorithms make transformation in the image in the spatial domain of the image and also the frequency domain of the image. In this example, we can see that the original size of the image is 12 kilobytes. We can compress them to 1.8 kilobytes. This means 85% of compressed information, and we can still distinguish the image. But when we try to compress a little bit more with the 96% of information, that means 0.56 kilobytes, we can see that the image starts to be, well, not correct, to be unrecognizable. We will start with the loosely compression method with predictive coding. This uses a quantifier. A quantifier is used to map or to trace the prediction error inside a limited range of values. There are two types. Well, actually, the loosely compression with predictive coding is also known as the differential coding. The difference between them is that the differential coding adds a quantifier. As we can see in the two schematics here, the top one, it's actually differential coding. We can see the quantifier, the symbol coder, and then the predictor. And on the bottom side of the screen, we can see loose compression with predictive coding. They only use predictor. They do not quantize. This means that they do not have a range of values to take for an error margin. Now, transform coding. This method actually applies for a transform to an image, and the coefficients obtained from this for the transform, they are quantized or discarded, and then they can be codified or compressed. And they work actually both ways. We have an input image, we have a transformation, a Fourier transform that we will quantize and then encode to compress an image. In order for us to be able to decompress that image, we will need to use a decoder. A decoder is the counterpart of an encoder. In a decoder, we will use the same symbol encoder that we use with our encoder. Then we will use the Fourier inverse transform, and then we will merge every image that we get. And this way we can decompress the image. The problem with these methods are basically that if we don't have a quantifier large enough to fit all values or to fit the range of values that we would like to keep in our image, we will lose information that we would want other way. And well, actually this concludes this little tutorial about compressing images. I hope you like it, and well, thank you.